In this video, we're going to discuss the energy of simple harmonic motion, and we're going to look at three examples where we can derive three different equations that build on each other. So, total energy just equals the kinetic energy plus the potential energy. We've known that from energy. But when we have a spring or an oscillation, we have to look at the kinetic energy and the potential energy due to gravity and of a spring in a spring's case. So if we have a vertical spring, let's say like this, right, with a spring, we have to look at the spring potential energy and the gravitational potential energy. And so the spring potential energy is given as 1/2 k, which is the spring constant, times the change in x, which is we have an equilibrium point. It would be like this squared. And so we're going to look at three examples for a horizontal spring so that we can derive some equations that you might want to use later. Okay, so let's first look at the energy at the amplitude. So let's say we had a box of mass m pulled to an amplitude of a. At this point, we know the velocity is going to be equal to 0, which means the kinetic energy equals to 0. But the spring potential energy is at a maximum because this is going to be the farthest change in x. It's the maximum change in x that we can get is when it's at amplitude. And so we can say we know that the energy total equals the spring energy plus the kinetic energy. But in this case, the kinetic energy goes to 0 and we have just our spring energy. So our E total will just equal our 1/2 k change in x, but in this case the change in x just equals the amplitude. So we have amplitude squared. And so this is our first equation. And so this tells us how much energy this system has at any point, because this total energy doesn't change. So even if the box is now right here, we still know the total energy is equal to this right here. Just instead of, it's not going to be change in x, it's going to be, still have to have the amplitude for the total energy. Okay, so this is a constant that won't change no matter what. You can just use this maximum point to derive this total energy. Okay, so let's look at a situation where we have at the box is at equilibrium. So let's say it's oscillating and right now it's at equilibrium. So at this point, we know the velocity is going to be at a max, which means the kinetic energy is going to be at a max, but the potential energy is equal to 0. And also note there is no gravitational potential energy because there's no change in height, so we don't have to worry about that. Yeah. So at this point, we can write our energy equation as the energy total equals the kinetic energy plus the potential energy. But we just said the potential energy is 0, so that comes out. And so now we can still use our equation that we derived before, as the total energy is going to be 1/2 k times the amplitude squared. And we know kinetic energy is 1/2 mv squared. But in this case, this velocity is the max velocity because we are finding the velocity in the center. So we can use this to derive an equation for the max velocity given the mass and the spring constant, the amplitude. So first off, these 1/2s will go ahead and cancel, and we can rearrange this equation for velocity. So we have v max squared equals ka squared over m, and so we can take the square root and get that the v max is equal to the square root of ka squared over m. And so we can pull an a squared out and take the square root to get v max is equal to a times the square root of k over m. And so that's our second equation that we derived. So now we can use this to find the v max of any situation if we know what the amplitude is, the mass, and spring constant. Okay, so now let's look at the energy in between this point. So we want to know what is the velocity it's traveling at any point x, given the amplitude and the max speed. So let's think about it as we have before. we know there's going to be some velocity that we don't know. We know there's going to be some kinetic energy, which we don't know, because we're not at any endpoint. So let's look at our energy here. So we have the energy total still equals the kinetic energy plus the spring energy, but we can't cancel any terms out here, so let's write out all of these. So we know the max is always going to be this Ka squared equals the max, or the normal kinetic energy, mv squared, plus the spring potential energy, K. In this case, it's going to be x squared because it's not at amplitude, it's at some point x. Right? This is at some point x. So now we can go ahead and start rearranging this a little bit. The 1/2 will cancel. And so we can rewrite this with, because we're trying to solve for a velocity, so let's write it with velocity on its own, with mv squared equal to Ka squared minus Kx squared. Okay, and then we can divide by the mass. So we get the velocity squared is equal to Ka squared minus Kx squared divided by the mass. Okay, so now let's pull out this first term right here. So what we're going to do is, I'll write this out so that it makes sense, hopefully, is I'm going to divide this m into here and into here separately. And then I'm going to pull out this Ka squared over m. So I'm going to factor it out. Even though there's not the Ka squared, we'll just have to divide by it so that if we multiplied it through, it would work. Okay? So I'm going to say the velocity squared equals this Ka squared over m. And then we can say 1 minus, so the Km just pull out. This x squared stays here. But now if we were to multiply it in to get the same thing, we would have to divide by an a squared. And so you can go ahead and check and multiply these back in and make sure you get this part right here. So I'm just pulling this out, which means you have to divide by this a so that when you multiply it in, they cancel. Okay, so now we have this right here. But you may notice that we want just the v in terms of x and a, and we still have this k in here and the mass. But what we can do is use this equation up here that we derived for the max velocity. So we know that V max is going to be equal to a square root of K over m. So what we can do is actually just square both of these, and we get that V max squared is equal to a squared times K over m. But this right here is just Ka squared over m. Just rearrange that, and we have this in our equation. So now we can go ahead and plug that in, and we get that v squared is equal to v max squared times 1 minus x squared over a squared. And so if we take the square root, we get v equals v max times the square root of 1 minus x squared over a squared, the amplitude. So now we have an equation for v at any point in the oscillation. And notice that if you're at equilibrium, your x will be 0, so you'll have the square root of 1, which is 1, so you'll just get v max. So let's look at this actually. So at equilibrium, we'll have v equals v max square root of 1 minus, we'll have 0 over a squared, and so that'll just equal v max square root of 1, which just equals v max. So at equilibrium, the velocity is at a max, which we know is true. And then if we're at the amplitude, then v equals v max square root of 1 minus the amplitude squared over the amplitude squared, which equals v max the square root of 1 minus 1, which just equals 0. So the velocity is 0, which we know at amplitude the velocity is 0. So that's kind of just a way to make sure we check that this equation works for points that we already know. So now we can find the points at any point along this x, what the velocity would be. Okay, so hopefully that was helpful. Leave your questions down below. This was the last video for Unit 7. So we only got one more unit left, and yeah, thanks for watching.